So I wanted to talk a little bit about binomial approximations and this idea of continuity correction. I've heard it come up a few times from a few students, how it's come up in lecture apparently, but you guys haven't had any real problems on it. So I can't speak to whether this is going to be on the exam or not at all. I have no idea, but uh, just in case, I wanted to talk a little bit about it because it seems like there's some confusions to what the idea of binomial approximation even is. And basically, the idea is just that we are going to approximate a binomial distribution with a normal distribution. So I have this pretty cool website that I found that just visualizes a binomial distribution. So you can see that the number of trials here is 4, and the probability of success is 0.5. And over here on the left, I can change that. I can make the probability of success bigger. I can make it smaller. Let's say the probability of success is 0.6. And then the number of trials, I can increase that. Because right now, you would look at this and you're like, how the heck can we approximate this like a normal distribution? Well, right now, the number of trials is just too small. But as we increase the number of trials, you can see it starts to look more and more like a bell curve. And if you don't entirely see that, I'll just fill in the, or I guess connect the dots here. So if I draw from the top of the bars, connecting them, and I'll do it kind of slowly so that, it's somewhat neat, then you can see this looks a heck of a lot like a normal distribution. And the main difference, though, is that a binomial distribution is discrete. And that means that the heights of these blue vertical bars, the heights are what represent the probability. And in a normal distribution for a continuous random variable, we think of the area under the curve representing the probability. So let's take, for example, that this value at 10, then we can see it has a height of about 0.18, I would say. So it looks like the probability that x is equal to 10 is equal to the height of the bar, which is about 0.18. And I'll just say it's 0.18 exactly for this purposes. But we can visualize this, instead of it just being a height, we can visualize it as an area if instead what I do is take a half step to the left of 10 and a half step to the right. So half step meaning this is 9.5 and this is 10.5. And now if I draw a rectangle that has the same height from these points here, then the area of the rectangle, well, an area of a rectangle in general is base times height. The height, we've just constructed it to have the same height of 0.18, and the base is 10.5 minus 9.5. The base is 1. So 0.18 times 1, this area is equal to 0.18, which is equal to the probability that x equals 10, where x is this binomial distribution with n trials and probability of success 0.6. But I'm going to draw a different area on this graph here. So let's instead let's draw these lines all the way up to the blue curve. So I'll draw it all the way up to the blue curve on the 9.5 and on 10.5, go all the way up till it touches the blue curve, connect that along the curve, and you can look at this area here. Now, this area is not going to be exactly 0.18. It's going to be pretty dang close. Not exactly. It kind of overshoots on the left-hand side from the green rectangle, and it undershoots on the right-hand side. And the overshoot and undershoot don't exactly cancel in a perfect way. But we could definitely say that the area is approximately equal to 0.18, which is equal to the probability that x equals 10. But what is this area exactly equal to? Well, this area is exactly equal to the probability where some random variable y is between, not 5.5, between 9.5 and 10.5. Where, well, what is this random variable y? This random variable y is the random variable that would have this normal distribution. So y is a normal distribution where what is the mean and what is the standard deviation of this normal distribution? Well, it's going to be the same as the mean and the standard deviation of the binomial distribution, because you can see it's centered above the same place. It has the same mean, and the standard deviation just kind of tells you the spread. And you can see the spread looks the same. Like we drew this curve by essentially connecting the dots of a binomial distribution. So the mean is NP. This is for a binomial distribution. And the standard deviation is the square root of n times p times q. And these are on your formula sheets if you don't remember them. And so n times p, well, that's 15 times 0.6. So n times 0.6. And then square root of n times, well, n is 15, 15 times 0.6 times 0.4, because q is 1 minus p. It's all underneath the square root. So we could crunch these numbers, and the upshot is that if we take this interval with a normal distribution with this mean and this standard deviation, and we compute this area, the purple area, then it approximates the probability that x exactly equals 10, where x is the binomial distribution, corresponding to the same n and p that we used here. And this idea of taking a half step down and a half step up from our target value. So our target value is 10. We went half step down and half step up. That is this idea of continuity correction for the normal distribution, because it is a continuous random variable.